the most stable quantum computer that already exists is the atom. Time has already proven that an atom can exist for millennia, essentially. And it's nothing other than a quantum computer.
Hello and welcome to a brand new episode of Engati CX. I'm your host Nimilika and we are very excited to have all of you join us today. On this show, we talk to CX and technology experts from around the world. We explore, uncover, and share fresh insights on creating experiences that your customers will remember and look forward to. Engati is the world's leading multilingual no-code digital CX platform available across 15 channels with 53,000 solutions created across 186 countries in every domain and use case. Engati has also been recognized as a top platform by Inc. magazine, Tech World, CIO magazine, and many others. Engati recently also won the Cody 2021 award for being the best AI-driven technology solution. We run the Engati blog, video channel, and the Engati CX podcast, receiving upwards of 400,000 visitors annually. Let us now welcome today's guest. As Chief Technologist at Deep Order Technologies, Dr. Pravir Malik has been developing a unified theory on mathematics of organization with applications in a range of complex adaptive systems. He has written 16 books related to this, which includes a recently completed 10-book series on cosmology of light to elaborate mathematics with implications in quantum computing, generation of computational strata, genetics, artificial intelligence, and transhumanism. Dr. Malik currently serves as an advisor to several organizations around the world. Welcome to the show, Dr. Malik.
Thank you, Nimi. Very pleased to be here.
We are excited to have you. Before we dive into our interview with Dr. Malik, don't forget to subscribe to Engati and tap the bell icon to get access to exclusive content from thought leaders from around the globe. What are the potential benefits of this new paradigm of computing, like in quantum computing?
I think that, first of all, to answer that question, one has to step back and ask, what is the medium in which the computation is taking place? Because that itself is going to determine what's possible with that kind of computation. Now, when we think about classical physics and when we think about our world as it exists right now, the visible world and the digital technologies that have emerged from it, it's due to a very deep understanding and a mathematics that we've created at the digital level that allows us to elaborate a whole range of different computational devices based on this digital paradigm. When we think about another paradigm or another medium or strata of computation, for example, our cells, living cells, whether in plants or in human beings or in animals, again, there's a vast amount of computation that goes on in these cells. And that is also due to this medium operating differently. So when we come down to the quantum realm, the question as to what's possible, again, is due to our understanding and a perception of how that medium operates. So a simple answer is that, yes, there's going to be vastly different potential that's possible from either the digital realm or the cellular realm, or even if we think about strata taking place at the atomic realm. So this is going to be fundamentally different. Why? Because the quantum realm, we know, operates differently. If we think about classical quantum physics, basically, then there's some phenomena that pop out. For example, like entanglement and superposition that has been written about a lot. And we already know that by considering those two phenomena or mechanisms, we can create computation that would be theoretically much more superior in some cases. It would be able to solve problems, do computation at an exponential rate as compared with digital computing. However, the real question is, what is the nature of the quantum medium? And that's where my point of view or perspective varies from perhaps what we've read about in common literature. And we can go into this I'm sure you'll ask me some questions related to it, but I'm going to briefly touch on this because I want to answer what's possible with the quantum realm. And if we think about the processes of matter and life as emergent from the quantum realm, since the quantum realm is the base of all physical manifestation, therefore we already have a quick idea that the kind of computation that's possible and the kinds of results that are possible because you have this quantum realm at the base of everything are going to be vastly different than any other possibilities that emerge from other computational strata. So it's going to be game changing.
Looking at all of these as realms makes it easier to understand or perceive the whole thing about quantum and the actual computation we are able to do now. How did it even start? How did physicists start thinking about this realm?
If we think about scientific research, then there's the whole process of penetration into deeper and deeper levels to understand what creates phenomena. When you enter into the realm of molecules, then you see that there's chains of molecules that will animate these molecular plans. They're structured differently, but you get into the nature of the molecule and you see that it itself is determined by a range of or diversity of atoms. And then when you penetrate into atoms, because you still want to understand what's making the atom tick, you of necessity will have to go into the quantum realm. And there, as theory and even experiment shows, that any atom is, in a sense, the result of four kinds of quantum particles. We have quarks, leptons, bosons, and Higgs bosons. And then the question is, when we try and understand what's happening at that level, we want to see how these different quantum particles emerge, disappear, and basically how they operate. And that gets us right into the notion of quanta, if you will. Now, I've taken a top-down approach here. By contrast, another way to understand quanta is a mechanism that allows information or energy to be gathered into a packet. And when that energy or information reaches a threshold value, then whatever is implied by that energy or information can express itself more materially. So quanta, when you look at it from the bottom up as opposed to the top down, it becomes a device by which some concept or information or energy can express itself concretely in packets. Any creation of quanta is fundamentally a creative mechanism. So I want to draw a contrast here between digital computation and quantum computation. In digital computation, we have the regurgitation of set instructions. Any programmer knows that, that's what animates any kind of computing device. And these instructions will follow just exactly what they're supposed to as per the program. Now, by contrast, when you look at quantum computation, we're not looking at something that's constructive. We're looking at something that's creative, that's fundamentally creative. Because the very notion that quanta takes some idea or concept and then can only express it when a threshold is reached means that there is something that is trying to express itself through the device of quanta. So it becomes a completely different way of thinking about computation. Because when we're talking about the quantum realm, fundamentally, matter and life are emerging from the quantum realm, and that's a creative act.
So when we spoke about quantum realm, what is the direct implication for quantum computing? How does quanta imply quantum computing?
Well, so there's a few different things. The things we've studied certain phenomena that take place in quantum computing on the quantum realm. There's well-known phenomena such as a superposition or entanglement or annealing or tunneling. And basically, a quantum computer can be defined as something that leverages any of these phenomena, these naturally occurring phenomena of the quantum realm, whether it's superposition, entanglement, tunneling, or annealing. If you've got a device that can predictably use those mechanisms, you basically have a quantum computer.
So these computers try to imitate these methods that you were telling us about.
Yes,
Okay.
exactly. So quantum computer can be defined very, very broadly. Any device that manipulates, that leverages these phenomena in whatever way, because these phenomena are supposedly occur only at the quantum level, whether it's superposition, entanglement, tunneling, annealing. If you've got a device that can predictably leverage that, then you essentially have a quantum computer. So a quantum computer is not just one way of thinking about the quantum realm. There are basically a vast number of ways in which these quantum devices or computational devices can be developed. And I think that one thing that I'd like to point out is that when we think about quantum computation right now or quantum computing devices, it's very easy to think that there's only one way to do it. In fact, there are many, many ways. And it also is determined by what other phenomena you may find at the quantum realm. Now, in the research that I've done, I suggest, and these are things I've written about, the 10-book series that you mentioned, Cosmology of Light. I've elaborated at a very deep level this notion of fourfoldness, which I see as a mechanism that occurs at the quantum realm. Why is this mechanism? So I'm proposing this mechanism that's different from superposition, entanglement, tunneling, and annealing. I'm saying it exists at the quantum realm, and it's a way to interpret how quantum particles actually express themselves and how they emerge and how they disappear and things. There's a kind of a logic that's different than just say probability or statistical based logic, and that's like a fourfold logic.
That is very, very interesting. So what are the challenges in designing practical quantum programs? And what are the main challenges in building a scalable software systems for quantum computing?
Well, if you think about any kind of technology stack, assume you've got just let's simplify it and assume you've got 4 layers that are required to create workable software or any kind of program based on the quantum realm. At the very first or fundamental layer, you've got to have hardware that can rightly interpret what's happening at the quantum realm. That in itself is a huge challenge because currently our approach to understanding the quantum realm is based primarily on what's called the Copenhagen interpretation of quantum mechanics. And in that interpretation, we assume that any quantum object can exist in infinite states, except when you measure it. When you measure it, it will collapse right away into one state. So by definition, in the Copenhagen interpretation, you can never understand what's happening in the quantum realm because the moment you try and measure something, it collapses into something observable. So from the infinity of possibility, it becomes one thing. And if you take that as your paradigm of quantum computation, then you can never really penetrate into the quantum realm. All you can do is perform a variety of statistics and probability to see what kind of phenomena is happening more often, and from there, intuit what might be happening in the quantum realm, right? So there's the whole hardware problem of how do you, first of all, what is the quantum realm? How do you read it correctly? And then based on that, what kind of device can you create that will capture what's happening in the quantum realm? So that's one fundamental problem. Then the next thing is that once you have that, you want to have a layer of control software that is able to manipulate this hardware, right? But if your hardware, if you first of all don't understand the quantum realm, then your control software is going to be much more narrow than what it possibly can be. And here I give a contrast. So for example, without getting too complex, I referred to earlier this fourfoldness, but let me give an example of that. So in a cell, there are only 4 molecular plans that are active. I call them polysaccharides, lipids, proteins, and nucleic acids. When you go into the realm of the atom, when you think about the periodic table, atoms are structured into 4 categories. You got S shell, P shell, D shell, and F shell atoms, primarily speaking. So again, it's a fourfoldness. When you go into the realm of quantum particles, again, all quantum particles are one of 4 kinds, either a quark, lepton, boson, or Higgs boson. Now, in the research that I've done, basically I link all four of these things so that I'm saying they're expression of one thing. So, and these all emanate from the quantum realm. The point being that if you perceive the quantum realm differently, then your hardware is going to be different. So the fundamental layer required for a technology stack is going to be very different. And then your control software is going to be different. And then sitting on the control software, you're going to have algorithms that you want to leverage that essentially take what's happening at the quantum realm, so what the hardware is able to perceive, and you want to manipulate in certain way to perform certain computations. And then on top of that, you've got to have application software that would then rightly use the layers below it to actually do what you want it to do. So it's a complex problem, and the complexity arises primarily from the fact that our understanding of quantum realm is at the moment very narrow if we take the classical understanding, which is just relies on this Copenhagen interpretation of quantum computation.
So if we, because of this Copenhagen interpretation, we are seeing a gap between the hardware and the software for quantum computing. So if we look at it in the fourfold method, do you say we'll be able to bridge the gap?
Absolutely.
Or will it take more time to do that?
No, I'll tell you why. There's several reasons. One, if we think about the phenomena I mentioned earlier, things like superposition, entanglement, tunneling, annealing, which essentially is what any quantum computer is trying to leverage in order to create, to do its computation and create output. Now, in the approach that we have right now, that companies like IBM and Google and Intel and Rigetti and whoever else are pursuing, they first of all assume a Copenhagen interpretation of quantum mechanics, and therefore by definition they're trying to create superposition and entanglement from the bottom up. They're trying to assess how a quantum particle might exist in multiple states simultaneously, but it's all from the bottom up. Now, if you take the fourfold approach that I have written about extensively, then essentially what we're saying is that as a result of that, phenomena like superposition and entanglement exist naturally. They exist in abundance. Therefore, when you are trying to compute something, it's not about creating superposition and entanglement, which is fundamentally unstable because you're trying to, there's a phenomena called decoherence when you're dealing with very small quantum particles. And the idea being that any kind of observation can essentially destabilize whatever you're trying to do. But if we take this fourfold approach, then since superposition and entanglement exist abundantly, there's no problem of decoherence, and hardware would be much more stable to begin with, because hardware is then essentially interpreting, generating, or trying to perceive this phenomena that already exist. I want to make one more point related to this, is that the most stable quantum computer that already exists is the atom. Time has already proven that an atom can exist for millennia, essentially. And it's nothing other than a quantum computer because it takes inputs, whether it's through energy or photons, it processes it, and then it creates outputs as light or, again, energy, whichever way that we want to do it. So any quantum computer that essentially leverages an atom as a basis, as opposed to whether it's, you may have heard of Microsoft approach, which is topological, to try and perceive something called the Majorana particle, which is very elusive. Or even if you think about IBM and you think about Google, they try to use superconducting circuits, but what the superconducting circuits are doing is that they're essentially magnifying results or some phenomena that's happening at the quantum level, which again is, since it's from the bottom up, it's fundamentally not stable, and therefore they have to create these computers at almost absolute zero temperatures, which becomes unpractical. It's not scalable. So if you take atoms and if you take a fourfold approach, then scalability doesn't become an issue. But you're looking at quantum realm completely differently.
So there are speculations about quantum computing having cybersecurity threats. How true is that? What is your take on that?
Well, so, of course, one of the supposed applications, which theoretically makes a lot of sense, is that cybersecurity would become less of an issue with quantum computation, because when you entangle two quantum objects together, you have a dedicated channel that nobody else can penetrate. If anybody tries to penetrate that entangled channel, then you can tell right away that somebody has penetrated it, and that channel can, in a sense, you detect that and reconfigure, or can just stop functioning. So there's no cybersecurity threat that can ever happen if you take that approach. So therefore, this becomes a huge application area if it can work, right? It may be able to work. I think there's already proven approaches where in very controlled arenas, you can have this entangled channel that nobody else can penetrate. But then the question is, how do you scale it and how do you make it actually usable by the general people like you and me, which is the whole different issue, right? I mean, so that's why people are talking so much about the application of cybersecurity when you think about quantum computing and specifically entanglement. If we assume that entanglement is an abundant phenomena and not something that's created from the bottom up.
There is stability because of entanglement, is what you were saying, right?
Exactly.
Yes.
Yeah. There is stability, and it exists naturally. It's not something you have to create. But the very fact that you have atoms all behaving the same way means that there's already stability in that process of entanglement. Right.
Anyway. Yeah. So what is the current status of research in quantum computing?
Well, it comes down essentially to this, and I've spoken about it in the last half an hour or so, but it's a function of how we fundamentally perceive the quantum realm. If we perceive it using the Copenhagen interpretation of quantum mechanics, then in my perception, research is already confined to a very narrow area, and the possibilities of what can happen with quantum computation is confined. If, however, we begin to perceive the quantum medium as something different, as something fundamentally creative, because as I've tried to suggest in this brief interview, all phenomena of matter and life have the same principles in it. There's a fourfoldness that emerges methodically, and therefore that can be extrapolated backward to the quantum realm. And if we take that as a possibility, it opens up infinite doors to the kind of research and advancements that can take place in quantum computing. By the way, I have filed for a patent based on a reconfigurable atom-denominated quantum computer that I've designed on paper, which essentially uses this fourfold mechanism, which I call quaternary interpretation of quantum computing, as a basis to build quantum computers. And so this is a work that have been doing for the last year or so. So I just
that's very
if
promising.
you take that point of view, the research frontiers open up tremendously. So.
Right. Are there any more sound bites that you would like to leave for the audience?
Well, I think the basic thing is that the quantum realm is, rightly, it's understood as something that's mysterious because it goes down into the smallest realms that we can physically understand or perceive. But that does not mean that realm that we, due to our instrumentation or due to our limitations that we perceive, is the start of everything. there might be something behind that realm which we don't understand yet. And the quantum realm becomes very interesting because it's, in a sense, a gateway between something that's behind it and something that expresses itself from it. And so to imagine that a quantum computer, the way that we're imagining it right now, can perform only a limited number of tasks in this realm that's fundamentally mysterious, I think is the biggest paradox of all. Because the quantum computer should really draw out that mystery and build on it. So that's what I'd like to conclude with from my point of view as kind of a thought starter for possibility.
That's lots of food for thought. Another question that I personally had, and I don't think Google rightly answered, you will be the best person to answer this now. Why do people say quantum computers will be the fastest computers of all?
I mean, this is well documented from a quantum, from a Copenhagen interpretation point of view. Theoretically, it's because of the phenomena of superposition and entanglement. So if you have a quantum object that can exist simultaneously in many different states, and if you entangle a quantum object with another quantum object, then it changes your paradigm of computation because you can process many more states simultaneously in different ways. And that's where the potential leverage exists for thinking about the extraordinary processing speeds from the Copenhagen interpretation point of view. Now, if you ask me, and as I've suggested in this, entanglement works differently, superposition also works differently. I haven't talked much about that. But these phenomena work differently. They are different than we perceive them. And so computation is going to be different as a result of that.
Thank you a lot for giving us your time, Dr. Malik. Your insights were really, really valuable, and I know our audience is going to enjoy this interview. We'll be back with a new episode with a brand new expert soon, so stay tuned, and we'll see you around for the next one.
Yeah.
Thank you.
Thank you. Thank you very much.